Let us go on now and show that if U is UIEI and V is VJEJ, then the components of the dyad can easily be found. We don't even need to do anything. The components of the dyad is just straightforward. So it's UI, VJ, EI, circle times EJ. You don't even need to go on to use the definition we just made. It is, in the case of the dyad, the component is obvious. If you want to go ahead and find it, and find that it is UI, VJ, you can go ahead. But that is the component of the dyad. But is there any question on the component of the dyad before I move on? Please, I want people in the class to tell me, is it components of the dyad as I've shown here? Is it very clear? If it's not clear, let me know. Then I can do some little more explaining. But it's obvious, so obvious to me. I hope it is obvious to you. Okay. Olajide Bito said it's obvious, it's clear. Anybody else? Okay, so the component of the dyad is a UI. Before I go on, there are two more things I want to do today before I finish the class. I want to define the product of tensors, composition of dyads, and then transpose of a dyad, and the idea of symmetry. I will stop on slide 25 today. So we have like 8 slides to go. And so I just want you to notice that I did not tell you that a unit tensor is defined by 100010001, like some textbooks will do. No, we define what an identity tensor is, what it does, and we proved that if it does those things it does, then its components will be 100010001. So we didn't use the components to define the tensor. We defined the tensor fundamentally, and then we showed that with that fundamental definition, those must be the components. Similarly, we define the dyad, and then we show what the components will be. So we are coming from the fundamental. The method we are using here is that everything is coming from the definition. So the definition is the important thing. All the other things you are trying to cram don't matter, because you can always get there if you understand the definition. So you can understand the definition and all those things become obvious. So many times, the reason why learning is very hard for you is because you are using the wrong method to learn. This cramming method is not as fantastic as it appears. It's just like it's a shortcut, but it doesn't really go to the depth of what's going on. Okay, we are going to talk again. We are going to talk today about, at this point, we are going to talk about products. When we want to talk of products of second-order tensors, let us first of all look at the products of zero-order tensors. Remember, a zero-order tensor is a scalar. When you say product, if I give you a scalar, let us say 2, and I give you another scalar, let us say 17, and I tell you, give me the product of those two scalars. One is 2, the other is 17. Let me see what you will say. One is 2, one is 17. Give me the product of those two scalars. One scalar is 2, the other scalar is 17. Oh, okay, 34. So you don't have any problem getting the two products of the scalars. I'm sorry, getting the product of the two scalars. It doesn't give you any problem. Okay. Suppose I gave you two vectors. If I give you vector A is if I let us put some numbers to it. Suppose vector A is 1i 1j, and 1k. That's vector 1. 1i, I plus j plus k. Vector 2 is 2i plus 3k. That's 0j. So vector 1 is I plus k plus I plus j plus k. Vector 2 is 2i plus 0j plus 3k. Now, did you get those two vectors? The vector 1 is I plus j plus k. Vector 2 is 2i plus 3k. Did you get those two vectors? Class, did you hear me? I'm giving you two vectors. Vector 1 is I plus j plus k. Vector 2 is 2i plus 3k. Now, class, give me the product of those two vectors. Give me the product of those two vectors. Okay, Oluwa Tobiwa Ekunife said, what type of product, sir? Okay, that is what I am trying to, that's what I expected to hear. You see, when we are talking about zero order vector tensors like scalars, the product is not ambiguous. There is only one product. There is only one product when we are talking about scalars. Multiplication means one thing only, nothing but one thing. Isaac Olaoye, you are wrong, because I didn't ask you for scalar product. I just said product. I didn't specify what product. So you cannot, how did you know scalar product I want? I just said product. Israel Olaoye, do you understand what I'm saying? I did not ask you for scalar product. I asked you for product. Israel, do you understand the problem I'm raising? Israel, answer me. Do you understand what I'm saying? Okay, so I am not asking for scalar product. I'm just asking for product. What I'm trying to prove to you is that once you are talking about vectors, the word product is ambiguous. You cannot just say, give me product. You have to say, give me multiplication by scalar, give me scalar product, give me vector product, give me tensor product. You have to put an adjective because there are more than one product when vectors are concerned. And vectors are just first order tensors. And we already have 4 different kinds of products. So because we already have 4 different kinds of products, anybody who wants product must be, when you are dealing with scalar, there is only one way to define a product. When you are dealing with scalars, there is only one way. There is one way only, and nothing but one way to define a product. You are dealing with scalars. When you are dealing with vectors, we have defined the scalar multiplication, the scalar product, the vector product, and the tensor product. At least 4 different ways exist in which you can take a product when we are dealing with vectors. Therefore, it is not correct. It is not a well-posed question to just simply say, give me a product when you are dealing with vectors. Similarly, when you move to higher orders, the matter becomes far more complicated. It is possible to define up to 10 different products when you are dealing with tensors. Not all of them are equally useful. Not all of them are necessary. But it is very easy. I can easily define 10 different fully defined products when I'm dealing with vectors. When I'm dealing with second order tensors. First of all, I can be multiplying by scalar. I can be multiplying scalarly by a vector. I can be multiplied tensorially by a vector. There are several ways I can be multiplying. So, but right now, we are going to deal with only just one product for now. We are going to come to those other products later. But just don't forget that products are not well defined when you go to higher orders. So this product we are going to deal with, we call it composition. We are going to deal with a particular product called the composition. The composition is a product, but it is a specific product. And I will define how it works. And we are going to deal with that right away. But what is important is that we have proved that the word product is only unambiguous when you are dealing with scalar quantities. When you are dealing with higher order quantities, the word product is ambiguous. And because it's ambiguous, you are compelled to specify what product you have in mind if you ask for product. The composition. The composition of two tensors produces a tensor of the same order. It is the product with no explicit operator. Some textbooks use the dot to denote composition, but anytime we use the dot, we are referring to two vectors. So we will not use the dot between two tensors. Given that S and T are tensors, the sequential operation of the two tensors on the vector produces a vector. The combined effect of the two is the composition of the two vectors. Let us say our two tensors are S and T. Let us say you first of all operate T on U. If you operate T on U, you get V. And you now operate S on V to get W. So it is, we define that as the operation of the composition ST on U. The composition ST on U is first of all operating T on U, then operating S on the product of TU. That is called the composition. If S and T are tensors and U is a vector, then by definition of the vector space, it is obvious that the composition ST will produce a vector W, which transforms a vector U to a vector W. Therefore, the composition is also a tensor of the same order. So ST is a tensor which operates by first of all operating T, then operating S. So when in the composition ST, the first tensor is what? I want you to go to the chat room and answer me. In the composition ST, which of the two tensors is the first one that you operate with? In the composition ST, which one comes first? S or is it T? Which is the first tensor in the composition ST? Okay, so you can see immediately that in the composition ST, the first tensor is not S, but is the second named, the second one named is the first tensor. So the first tensor there is T, and S is the second tensor. If you want S to be the first tensor, then you are looking at the composition TS. The composition TS allows you to operate with S first and then with T later. So if I ask you to operate to tell me the composition of the tensors that allow you to operate with S first and T, the answer is TS, not ST. So we are starting with the composition. Okay. Now, what happens when you do the composition of two dyads? If you do a composition of two dyads, let us say the first dyad is EI and EJ, and the second one is E alpha and E beta. Let us say these dyads are all autonomous, are all basis tensors. What do you have? You will see that if you operate it, if you first of all operate the EI and EJ, you see that it is EJU EI. And then if you operate this thing on, if you go to the second line, you see that you open EB and EI, and at the end of the day, what you have is E beta dot EI, E alpha, E beta dot EI, then E composed with EJ. If you look at the last line, if we do a very simple gymnastics here, you will see that we don't need to go through all the steps. Whenever you are taking the composition of two dyad bases, all you need to do is to take the furthest, is to do a composition of the furthest apart, E alpha and EJ. The two that are furthest apart, do a composition of them, and do a dot product of the two that are next to each other. If you do that, you are going to get the same answer. That's the shortcut to the answer. So the composition of this is simply the composition of the two that are farthest apart, that is E alpha and EJ, with a dot product of the two that are near each other, which shows that the composing two dyads has the same effect as obtaining a dyad from the two extreme base vectors, E alpha and EJ. In this case, scaling the result by the dot product of the near vectors, E beta and EI. This is a result we are going to generalize, but just watch and make sure you understand this result very well before we generalize it. So let me pause for 30 seconds. Take a look at this. If you have a problem with it, let me know. I will explain further. But if you have a problem, let me know. Okay, so move to the next slide. So because of that, because of the result we have just got, we can easily form the components of any composition. Let us say you do S and T. You know that S is simply S alpha beta E alpha circle times C beta, and T is simply Tij EI circle times EJ. So if you take S alpha beta and Tij, which are scalars, out of it, you are now left with composing E alpha beta and E alpha E beta and EI EJ. And you know that to compose this is simply take the dot product of the two near ones, we give you delta BI and then E alpha EJ. If you take that out and you operate delta BI on this, you see that it gives you SI alpha S alpha I Tij E alpha EJ. Or you can write it as SIK Tkj EI EJ. Please confirm that you understand every line here. I will pause again for 30 seconds. And if you have any difficulty with any line in this equation, go to the chat room and complain there so that I can respond to you. The result of the product of two dyads in this section can be generalized to a larger number of dyads. But right now, you can see that we have used that dyad trick to give the composition components of two tensors. If you have two tensors, you can get the composition, you can get the components of the composition. And I want you to take a look at this. It is SIK EKJ, which is S1, SI1 E1J, SI2 E2J, and SI3 E3J. So it's those three things that are available in each one of the 9 components. So these are the components of the composition. Now, assuming we are okay, so suppose we have a chain of dyads. So you have AI1 circle times AI2, where AI1 and AI2 are vectors, where AI1, AI2, all the way to AIN are all vectors. So suppose I therefore have AI1 circle times AI2, AI3 circle times AI4, AI5 circle times AI6, all along until I get to AIN-1 circle times AIN. If I have this chain, this very long chain, we can get their composition, the composition of the entire long chain. By doing this, it can be shown to result in simply taking the first and the last vector operands, and then multiplying that by the scalar product of the other vectors. You see, we take this first and the last, and we take the tensor products of them. That is, the first one is AI1, that's one, and the last one, circle times AIN. And then all the ones that are near each other, just take their dot products, AI2, AI3, AI4, AI5, and all are near each other. This is the answer. Reducing any tensor to a weighted sum of dyads is one way to simplify analysis, as the dyads are much easier to deal with for this and several reasons, as we shall see. So, because it is so easy for us to deal with dyads, so we are dealing with dyads of the coordinates. So every time we don't want to work with the tensors directly, you want to work the tensors expressed in dyad form. If it is possible to express them in dyad form, and it's always possible because you cannot, if you cannot quickly express them in dyad form, take their components, and their components are in terms of the dyad basis, so they're in dyad form. Look here. So you can see here, S is in dyad form and T is in dyad form by expressing S and T in their components. So you can always, given any tensor, you can always get the dyad form of the tensor because that is the easiest way to deal with tensors. It's better to deal with dyads than to deal with general tensors. So we have dealt with components of tensors. We have dealt with components of tensors. We have dealt with components of dyad. We have dealt with products, and then we have looked at the composition. We have looked at the composition of this, and we have looked at components of the composition, and we looked at components of a chain of dyads. So we have two topics more. The first one is the transpose, and the second one is the matter of symmetry. For those of you who remember your background in matrices, you look at the fact that you know what transpose means. We are going to define a transpose of tensors, not in terms of their matrix form, but in completely different terms right away. We are going to define them in completely different terms. And you can derive anything that you want from this. And take note, this definition is fundamentally important, and pay attention here. Given any two vectors and tensors S and T, S is called the transpose T if this happens. If U dot SV is written as V dot TU. If this equality is true for any two vectors U and V, then we say the tensor T is the transpose of vector S. This is the definition of the transpose. If U dot SV is equal to V dot TU, it is customary to use the same symbol for a tensor and its transpose. Accordingly, the transpose of S will be written as ST, just like we write the inverse of S as S to power minus 1. We are not raising S to power minus 1, it's just a way to write the inverse. And here we're not raising S to power T, that's the way to write the transpose. So by virtue of the definition of transpose here, if S is the transpose of T, then T is the transpose of S. This becomes very interesting in a dyad. Given a dyad A circle times B, for any two vectors U and V, U dot A circle times BV is written as U dot A B dot V, which is written as V dot circle times B circle V dot B circle times. This shows that transposing a dyad is simply the swapping of its operands. That is, the transpose of A circle times B is written as B circle times A. So when you are dealing with a dyad, taking a transpose is simply just reversing the order. To transpose a dyad, we simply reverse its two constituent vectors as shown. Once a tensor is in the component form, as it is expressed in terms of dyad, the transpose is readily obtained. Lastly, we can now deal with the issue of symmetry. A tensor indistinguishable from its transpose is said to be symmetrical. The tensor S is symmetrical if S is equal to ST. That is, if S ij EI circle times EJ is written as Sij EI circle times EJ transpose, which means you reverse EJ and EI, which is written as Sij EJ circle times EI, which is written as Sji EI circle times EJ. So that symmetry implies Sij is equal to Sji. That is where we are going to call it a day today. I want you to prepare for next class by reviewing today's lecture, going to your self-test and walking through some things there, and then read the rest of the chapter. There are about 12 to 14 pages to the end of this set of slides. And we are going to be looking at functions of tensors next week. So prepare for that by getting ready. So prepare. So we have how many pages now? We have 13 pages to go. But we're going to spend quality time on what we have next week, because the function of tensor is a very important issue, and it is better we focus on it without distraction. But it will depend on the knowledge of what we have today. So make sure you understand what we did today. And if you have questions, post them, and then see you next week